Welcome. We're going to jump back to something in chapter 12 called the binomial theorem. And you may wonder what the binomial theorem has to do with what we're doing in chapter uh, 14, with ways of counting and creating sample spaces. But we will make that connection as this video series progresses. So pay attention and take some notes. Okay, so off to the left, you see some binomials. A binomial is simply a form of polynomial that has two terms, hence the name binomial. And we want to expand those to different powers, right? Now, it's pretty easy to see anything to the 0 power should equal 1. So I'm going to write that in the middle of the screen for a reason. Now, if I had a plus b to the first power, well, anything to the first power is just itself back again. So we have 1a plus 1b. We don't write in the ones typically. You may remember when we square something, we end up with a squared plus, we would end up with twice the middle term, 2ab, plus b squared. So once again, that's 1 times a squared. And then there are a 2 in front of the ab term and 1 back in front of the b squared term. Now note, all of these terms are degree 2. So this is kind of the degree 2 row or second degree row because we have 2 factors of a factor of a, a factor of b, and 2 factors of b. So there are 2 factors in every single one of those. We're about to move to the degree 3 expansion. So if we cube it, we end up with a cubed plus, you may not remember this one, 3a squared b plus 3ab squared plus b cubed. All right, now if you don't remember this, what you can do is you can take a plus b and square it, which we had just done, and then we could multiply that by a plus b. So we could take the 3 terms in the previous answer, distribute the a plus b as we expand, and once you combine like terms, you will in fact get what I have in black. Then we could do the same thing. We could take what we have in the third row and multiply it by a plus b again, and after simplifying, we would end up with a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. Now, once again, notice that this is the degree 4. Every single term is degree 4. In this row, everything is degree 3. So usually we favor the first term of the monomial, or I'm sorry, of the binomial. And so we start with an a cubed, and in this row, and then as a drops in power, b goes up in power, so that the overall power of each term remains at 3 in that row and 4 in the next row. So we'll always start with all the powers of the first term. So in this row, we start with a to the 4th. We keep dropping a by 1, but bringing b up by 1 to compensate, and we get down to the end and we have b to the 4th power, all right? Now, there's a pattern in the numbers, all right? Remember, it's 1s in front of just a's and b's, but then we have the number 2. We have these 3s, and these 4s, 6, and 4, all right? And if we can see a pattern, we may be able to expand everything. All right, and this pattern is called Pascal's triangle. If we see the pattern, we can quickly expand things like a plus b to the 7th power, things that make it very difficult if we don't know the pattern. So if I were to write what we have so far in terms of numbers, you may notice a pattern. In fact, pause the video and stare at this for a few moments and see if you can figure out the pattern. Okay, so there's a connection. If you look at the 2, it had a 1 and a 1 diagonally above it. Well, 1 plus 1 equals 2. 1 plus 2 is 3. and 1 plus 3 is 4, and 3 plus 3 is 6, and 3 plus 1 is 4 again. So let's see if we can keep the pattern going. We always have ones on the outside, so let me figure out what would happen if I had a plus b to the fifth. There must be a 1 here. 1 plus 4 is 5, so there must be a 5 there. 4 plus 6 is 10. We would get 10 again, 5, and 1. So those would be the coefficients if I wanted to expand a plus b to the fifth power. And this is actually pretty quick if I want to keep going. 1, 6, 15, 15. Oh, I'm sorry, that's a 20. 10 plus 10 is still 20. This is a 15, a 6, and a 1. So we could expand something to the sixth power. Now this is useful if we have low numbers of powers. We can pretty quickly reconstruct Pascal's triangle. But you can imagine if we wanted the 100th power or something like that, it would be a bit time consuming to construct all of Pascal's triangles. So we want to come up with some patterns of what would always work based on these numbers. But Pascal's triangle is a quick way to remember if you needed to cube something or take something to the fourth power. The fastest way to do it might be, if you had a binomial that is to reconstruct Pascal's triangle.